Hi, I'm Margret. In this video I'm going to show you how we can determine the time complexity of an algorithm through benchmarking. When we benchmark, we start by warming up the JVM, that's the Java Virtual Machine. Then we are going to measure the execution time for a given input size, and then we repeat that for doubling input sizes. And to increase the accuracy, we're going to run the code with a given input size, not just once, but multiple times, and we're going to average the results. So let's get started. Here is a Java project I already started. It's called Merge Comparison because in the class exercise, we are going to compare the execution time of two different implementations of merge sort, but in this video, I only show it once. And we already created a method called getNumbers. So this method returns an array of the specified size, and it is filled with random 7-digit numbers. So at this point, we're going to start by warming up the Java Virtual Machine to trigger just-in-time compilation. This helps avoid unrealistically slow execution during early runs by allowing the JVM to optimize frequently used code. In our case, the frequently used code is the merge sort method that we're going to run over and over again because we want to figure out the time complexity. So let's get started here. I'm going to have a for loop, and I'm going to do this a couple of times, maybe like 8 times. And what are we going to do? We're going to run the merge sort. So here I have merge sort, and now I have to provide an array. Now needless to say, I don't have the array yet, so we better create that. Integer array is an array. So here I can say get numbers of a given size, and I can just say that's my initial size. And I make a variable for my initial size because we might need to adjust that. I'll talk about that a little bit later. But for now, let's just say I have here my integer initial size. And let's just say I start with 5,000. Why not? By the way, here I already have the output of a running version. I thought I wanted to show you that up front so you can see what we are planning to do. So we are going to execute the merge sort with arrays of doubling size, and we are going to measure the time it takes in seconds. So in this case, I was displaying 6 digits after the decimal point. We might just display 4 digits, but those are details. So the idea is we want to have a nice tabular output that shows the size of the array, which needs to double, and which shows the time we measure. So for now, I'm going to clear that, because we are now implementing the code, and then we're going to recreate something similar. So here we have the warm up. I'm going to make a little comment here, warm up JVM. And at this point, I have my Java Virtual Machine warmed up. Now I want to find out how long does it take to sort an array of a given size. So I need a variable size. It starts with the initial size, but we are going to double that size. So I create myself a variable size because that needs to change as we keep running our time measurements. So here I have my initial size. Now I want to know how long does it take to sort an array of that given size. So let's make sure we have an array of the given size. My array is get numbers of my given size. And now I want to measure the time. I can measure the time using the nanotime from system. So here I have system nanotime, and notice that nanotime gives you a long value. So I'm going to store that in a long variable, and I say this is my start time. And then I'm going to do something, namely sort the array. And then I am measuring the end time. And the duration or the elapsed time is end minus start. So if I subtract start from end, then I know how long it took to sort the array A using the sort method from class merge. I have my elapsed time, and my elapsed time is end minus start. And this time is still in nanoseconds because this is nanotime, so it's going to be really large numbers. But when we display the time, it is really helpful if the number is not that large. It's much easier to see a pattern, so we want to display it in seconds. In order to convert nanoseconds to seconds, we have to divide it by 1 billion. And I'm going to create a variable here. Those of you who like scientific notations might do something like this, which is perfectly fine as well. I'm going to spell out the 1 billion for those who find that easier to read. Notice the underscores. Java allows us to use that as a thousand separator. I strongly recommend, if you have large numbers, use the underscores because that makes it easier to get it accurate and make sure you have your 9 zeros. So here I have my billion. And now I'm going to print this. So here I have system out printf, and we are going to print maybe something like 10d, 1, 2, 3, 4, a couple of spaces. Then I'm going to print %f, maybe .4f. I told you I might change it to 4 digits after the decimal point. And then I want a new line. And here the first number I want to display is my size. So here is my size. The second number I want to display is my elapsed time in seconds. So here I have my elapsed time divided by billion. Notice elapsed time is a whole number, billion is a whole number, so this would truncate. I need to make sure that we get a double value because we want the digits after the decimal point. So I need to cast my elapsed time to a double. Let's see how this looks like. I'm going to run it. If I sort an array of size 5000, it took me 0.0012 seconds. If I run this again, I get a similar value. At this point, we measured how long it takes to sort one array of a specific size. Now we want to measure multiple arrays of doubling array size. So let's do everything we've done, not just once, but multiple times. For integer I 0, I is less than. Now I have to decide how often I want to do that. Let's make a variable out of that and call it benchmark rounds. And so here we're going to do whatever we planned to do before, not once but multiple times, and we're going to make that a variable. So let's just say we have benchmark rounds, maybe 8. 8 seems like a good number. So needless to say, I want to have the initialization of the variable size outside, because here at the end, after printing, I want to increase size. So I say here is my size, and now it needs to be multiplied by 2. Let's try this again. So we initialize the size with an initial size. We're going to create an array of the given size. We measure how long it takes, and then we're going to display it. And I'm going to run that. Here you can see the output. The left column shows the doubling input sizes. The right column shows the corresponding sort times. Now, in this case, I can see an outlier right here because it takes less time to sort an array that is twice the size as the prior array. So that is already a red flag that tells me something doesn't seem quite right. And such irregularities can be caused by system noise, especially when the runtimes are too short. So we want to make sure we have large enough runtimes to avoid misleading results. In order to determine the time complexity of my algorithm, I am looking at the growth rate of my sort times, and I want to have data that is as conclusive, as consistent as possible. So I'm going to start by showing you a table that allows us to look at the results and then conclude what time complexity we're working with. So here it says, well, if the sort time doubles, provided my input size is doubling, that is really important, and our input size is doubling. If the input size is doubling and the sort time is doubling, that means we have linear time complexity. If the input size is doubling and my sort times are quadrupling, that would be quadratic time complexity. Let's see what we are seeing right here. And I told you that the data is not ideal yet because we have this strange outlier. But when I look a little bit further down, I always try to focus on the larger sort times. I can see that here we have more than doubling. 2695 is more than twice 1124. So if I have sort times that increase by a factor of 2.2 to 2.7, that indicates linear arithmetic time complexity. That makes sense because the expected time complexity of merge sort is linear arithmetic time complexity. But we also want to make sure that we have data that allows us to support that. So here's a second table I want to show you. These are guidelines I use in my CS2 class. So if I have reason to believe that I am working with linear arithmetic time complexity, I try to choose an initial size for my array so that I end up with my largest sort time that is greater than a second. Now, if I would work in a context where I have quadratic time complexity, let's say in selection sort that is reliably in quadratic time complexity, then my sort times grow so quickly that I might try to have an initial size so that my slowest sort time takes more than 4 seconds. Now, if I have linear time complexity, I might not be able to reach this 1 second because linear time complexity can scale so well that I might run out of memory before I reach this 1 second. So I can be content with a shorter sort time, especially when I have logarithmic time complexity, which scales even better. And then if I have constant time complexity, I just have however long it takes because it's independent of my input size. So in this case, I know that I'm expecting logarithmic time, so I try to adjust my initial time so my slowest time measurement is greater than 1, and this will give me a better sequence of sort time increases to observe the expected sort time increase of 2.2 to 2.7. So I'm going to adjust my initial size. I started with 5,000 because at the beginning I was just starting with a good guess. Now I know if I want this number to be bigger than 1, I need to double it twice. And so here I will double twice my initial data. That takes me to 20,000. If I run it again, I would expect that my largest sort time should be more than 1 second, and it is. The other thing it does for me is I have a better sequence of numbers that shows me that we are more than doubling. So here from this value to that value, we are definitely not quadrupling, but more than doubling. From this value to that value, we're definitely not quadrupling, but more than doubling. And again, from here to there, we are definitely not quadrupling, but more than doubling. So I can say with confidence that I am observing here linear arithmetic time complexity. At this point, we have been measuring how long it takes to sort random arrays of specific sizes. However, Individual measurements can be affected by random system noise, for example, background processes, garbage collection, etc., and also by input variations. Since we are creating random arrays, some arrays may be nearly sorted, others may contain many duplicates, etc. To reduce the impact of these factors and increase the reliability of our benchmark data, we're going to run each test multiple times and average the results. So here, inside our benchmark rounds, rather than just creating one random array and measuring the time for this one array, we're going to create multiple arrays. So I'm going to use a nested loop. For integer j is 0, j is less than, I call it num trials, that's the number of trials. And we are going to run multiple trials and then determine the average time for all those trials. So here I need to create a variable. Let's make this 8 as well. And let's not just calculate the elapsed time, but we are going to calculate the total time. So here, the total time is going to start with 0, and then every time we are going to measure how long it takes to sort a specific array. We are going to add that to our total time. And so here we have the, let's take this out. So here we have our total time. We are adding how long it takes to sort each of those num trials, in our case 8, are random arrays of the specified size. And then at the end, I don't want to print the total time or the elapsed time, but the average time. So here I'm going to create another variable. I'm going to make this a double. It's my average time. And the average time is the total time divided by the num trials. And here I have my average time. This is a double, but total time is a long. Num trials is an int, so with two whole numbers, this would result in a integer division, a whole number division, which truncates. So I'm going to cast my total time to a double. Now here, of course, I no longer need to do any casting because my average time is already a double. And now I'm going to divide the average time by a billion because we want to make sure that our data is displayed as seconds. So let's run this. You can see the execution is a little bit slower because every time we have a large array size, we're not just creating one array and measuring one array, but we're creating 8 of them, measuring 8 of them, and then displaying the average time it took to sort the array of the given size. And you can see that we have a nice consistent growth rate here in the larger numbers. There's one last thing. I'm a big proponent of having clear descriptive output. So I am going to add here, and I prepared this just to save us some time, some additional information, a header that tells us the left hand side is the size, the right hand side is the average time in seconds, and we are benchmarking merge sort. So let's run this one more time. For one last time, I'm going to show you this table here, and you can see it's growing more than twice as much, more than twice as much, more than twice as much, significantly less than 4 times as much. So a growth rate of 2.2 to about 2.7. That lets us know that we have linear arithmetic time complexity.